Hi, welcome to this video on relative velocity vectors. And what I've got here is a swimmer swimming across a river from A to B and back from B to A. Now the river is still, that is that there is no current. So we say that this swimmer is swimming in still water. And that means that the swimmer has no problem going from A to B and back from B to A. Just points himself in that direction and, as I say, experiences no problem. But what happens if there is a current flowing in the river? Will the swimmer be able to still go from A to B with ease? Well, that's the aim of this video. So if the swimmer decides to swim from A to B and there's a current in the river, then what happens is that it gets carried downstream. So why is this? Well, if we look at the swimmer's velocity when he's swimming in still water, illustrated by this red vector, we saw earlier that he had no problem swimming across the river from A to B in still water. But then when we had the current moving from left to right, illustrated by this blue vector, then when the swimmer wanted to swim across the river, the velocity of the swimmer in still water, illustrated by the red vector, combined with the velocity of the water, illustrated by the blue vector, resulted in the swimmer swimming at this angle here, with this velocity. Let's just run that through again. So we can see now that as the swimmer starts off heading towards B, then the combination of those two vectors makes him go at this diagonal course downstream. Now suppose the swimmer wants to swim from A to B. How's he got to go? Well, he's got to head upstream. He's got to aim upstream. And if this is his velocity in still water, if there was no current, then if we look at combining the vectors of the water, the velocity of the water, with the velocity of the swimmer in still water, we would get an effect where the swimmer can swim directly across the river, providing he can swim hard enough to overcome the velocity of the water. The combination of his swimming in still water with the velocity of the water results in the velocity of the swimmer heading across from A to B. Let's have a look, see how that happens. So you can see that that combination there allows the swimmer to swim from A to B. Now, let's just do a few calculations. Let's suppose that the swimmer can swim at 1 meter per second in still water and the river flows at 0.6 meters per second. Then let's work out the velocity of the swimmer in each of these scenarios. And we'll start off with this one here. So if we're drawing the vector triangle, we start then with the velocity of the swimmer, which we mark in as a velocity vector, 1 meter per second, going straight across the river in the direction A to B. And then we've got the velocity of the water, left to right here, going at 0.6 meters per second. And then the resultant velocity of the swimmer, indicated by this black vector, we'll call it V. So how are we going to work out V? Well, that's easy because all we need to use is Pythagoras' theorem. Remember, V squared will equal 1 squared plus 0.6 squared because it's a right angle triangle. And so to work out V, then we just take the square root of 1 squared plus 0.6 squared. And if you work that out, you'll find that you end up with 1.166 and so on. And if we round that, say, to one decimal place, that'll be 1.2 meters per second. And when it comes to the angle, say, the angle made with the direction AB. We'll call that angle, say, theta. Then what would theta be? Well, we can do that from trigonometry. This would be the opposite side. This would be the adjacent side to theta. So it would be tan theta equals 0.6/1. And so theta would be then the inverse tan of 0.6 divided by 1. And if you work that one out, you end up with 30.963 and so on degrees. If you round that, say, to 1 decimal place, you're going to get 31.0 degrees to 1 dp. So from your basic triangle, you should be able to work out various quantities, generally by using Pythagoras' theorem or trigonometry. And for the other scenario where the swimmer has to swim upstream in order to travel across the river from A to B, then we would have our vector triangle as you've got up here. Let's just draw it in again. We'll put in the velocity of the swimmer in still water. That's 1 meter per second. We've got the current bringing the swimmer back on course going from A to B. This is 0.6 meters per second. And you've got the resultant velocity then of the swimmer. Call it V. So to get V again, all we need to do is Pythagoras' theorem. But remember, this time, this is a shorter side in this right-angled triangle. So it will be V squared will equal 1 squared minus 0.6 squared. So we end up taking the square root of that. So V equals 1 squared minus 0.6 squared. And if you do that, you'll find you get exactly 0.8 meters per second. And for the angle that the swimmer has to take, let's just say it's this angle in here, we'll call it alpha. Then to work out alpha, basic trigonometry here. Now that we know all three sides, you could use any trigonometric relationship, sine, cos or tan, but I'm going to go for sine in this particular one, just purely because I was given these two sides. So the sine of alpha equals opposite over hypotenuse, 0.6/1, so therefore alpha must be equal to the inverse sine of 0.6/1. And if you work that out, you end up with 36.869 and so on degrees. And if we round that to, say, 1 decimal place, it's going to be 36.9 degrees to 1 dp. Okay, so I hope that's given you some idea then how you can handle problems of this particular type.